We will start our problem with a semicircle. Then, inside this semicircle, we will inscribe a right-angled triangle which has the area of 32 squared units. Then we're going to connect the apex of this triangle with the left angle of our semicircle, and we're going to get another right-angled triangle with the area of 8 squared units. Now the question is, can we somehow calculate the area of this semicircle? This problem was sent to me by one of my subscribers who wanted to stay anonymous, so we're going to respect his decision. But if you guys want to try this one out for yourself, you can pause this video right now, try it out, and then come back and check the solution. Alright, so let's solve this one. So first, let's take a look at the big triangle which consists out of those two triangles inside. We can use the inscribed angle theorem, which states that an inscribed angle inside a circle is always 2 times smaller than the central angle that subtends from the same chord. As you can see on the sketch on the left, we have a semicircle, which means that the central angle must be 180 degrees. So this means that the inscribed angle at the top must be 90-degree angle. This is important because with this we know that our big triangle is actually right-angle triangle. So let's label its height as h, and we can label 2 segments into which it divides the hypotenuse or the diameter of our semicircle as p and q, as you can see on the sketch. Now from here we can use multiple approaches to find the connection between the height h and those segments p and q. In this video I'm going to show you 2 methods. The first method is using geometric mean theorem. This theorem states that if we have a right-angle triangle with the height h and the segments of p and q, we can say that the square of an altitude is equal to the product of 2 segments into which it divides the hypotenuse. And as you can see, this is exactly our case on our sketch on the left. Of course, if you don't know the geometric mean theorem, you can always use this method number 2, which uses the intersecting chords theorem. This theorem states that if 2 chords intersect inside a circle, the product of the lengths of their respective segments are in fact equal. So, if you take a look at our sketch on the left, we can shrink it a little bit and we can use the semicircle to complete the full circle. Then we can just mirror our triangle on the bottom. In this way, we will have 2 intersecting chords. One will be horizontal with the segments of p and q, and the other one will be vertical, which has 2 segments which are equal to the height of our triangle, and we're going to label it as h as before. So this means that h times h must be equal to p times q, or h squared is equal to p times q, and as you can see, we got the same conclusion as before. Alright, so now let's clear our image. And let's take a look at the right-angle triangle on the right. We know that the area of the triangle is equal to the base times height over 2. In our case, this is q times h over 2. But we also know that this area equals to 32. Now we can just multiply this with 2 to simplify, and we will get the following. From here, we can conclude that h must be equal to 64 over q. Now let's take a look at our triangle on the right. We can use the same formula for the area of the triangle, but this time it will be p times h over 2, and this area will be equal to 8. Of course, again we will simplify everything with 2 to get rid of the fraction, and we can get that h is equal to 16 over p. Now, since both of those equations are equal to h, we can actually say that those 2 equations are equal to each other. So 64 over q will be equal to 16 over p. Now we can cross multiply them, and if we simplify both sides with 16, we will get that Q is equal to 4P. Now this is going to be really important, and we're going to save this equation, and we're also going to save the equation where P times H is equal to 16. Now we're going to use those three equations. First, we're going to combine first two equations by substituting the value of Q from second equation into first. And if we do this, we will get the following. This means that H squared is equal to 4P squared, and from this we will get that H is equal to 2P. Now we can just implement this value into our third equation, and if we do this, we will get the following. Of course, we're going to work through this and get that 2p squared is equal to 16, and when we simplify with 2, we will get that p squared is equal to 8. Alright, so now let's take a look at our semicircle once again. We can label its radius as r. So now our blue line on the sketch represents the diameter, and it is equal to r plus r, or it is equal to the sum of the segments of P and 4P. So this means that 2r equals to 5p, which means that r is equal to 5p over 2. Now, remember, we are looking for the area of our red semicircle, and the area of semicircle is equal to the 1/2 of pi r squared, so we can just substitute the value of r. If we do this, we will get the following. Now we can simplify this, and we can group this and get that our red area is equal to 25p squared over 8 pi. But we already got the value of p squared, so we're just going to substitute it into our formula and get the following. Now we can simplify 8, and we will finally get that the area of our red semicircle is equal to 25 pi, and this is our solution. So I hope you guys enjoyed this problem. If you did, please do not hesitate to leave a like, share the video, and of course subscribe for more content like this. And if you found another way to solve this problem, please write it down in the comment section as you always do. And until next time, see you all and take care.